In this video, I would like to provide a short overview of what STEM education is all about, some guiding principles during STEM implementation, the different STEM practices, the 3 approaches to integrated STEM, and some additional guidelines. Hopefully this will help us in our own journey in implementing our STEM program this year. The information from this video is from this awesome book called STEM Lesson Essentials, Integrating Science, Technology, Engineering, and Mathematics, written by Joanne Vasquez, Carrie Snyder, and Michael Comer. Whenever I refer to a book, this is the book I will be referring to. First, let's start with the definition of STEM. There are many different interpretations out there of what STEM is and how educators use it in different contexts. But we will be using the definition of STEM from the book, which is interdisciplinary approach to learning which removes the traditional barriers separating the 4 disciplines of science, technology, engineering, and mathematics, and integrates them into real-world, rigorous, and relevant learning experiences for students. Our program will try to not only integrate science, technology, engineering, and mathematics, but also social studies, language arts, art, music, and other disciplines. The first goal is the obvious one, the one that many educators use to justify the implementation of STEM, which is to help students function and thrive in our highly technological world, and help the country remain competitive in the global economy. According to the National Resource Council's report called Successful K-12 STEM Education, STEM education develops understandings and capabilities that are required of personal decision-making, participation in civic and cultural affairs, and economic productivity. The second goal is not as recognized as the first, but I believe is extremely important, which is the connection between disciplines. The application of this idea creates opportunities for students to gain deepened conceptual understandings and develop valuable skills that can be applied in different contexts. The integration of disciplines shows students that finding solutions to engaging and meaningful problems require the use of knowledge and skills from different disciplines, all working together, interconnected and intertwined. Think of disciplines as gears, all working together for one common purpose. The book provides some STEM guiding principles. First, focus on integration. Like I talked about previously, we need to help students see the connection and close relationship of concepts, helping them connect concepts that may seem disjointed to them. Second, establish relevance. This idea is emphasized throughout the whole book. It is our job as educators to explain why the knowledge and skills learned is useful, why they should care. It is easy to explain relevance when students are given real-world problems, current event situations, global issues, or any appealing event. Third, emphasize 21st century skills. The workplace our students will enter requires a workforce that can access information, solve problems creatively, and collaborate with others. Next, challenge your students. You want to give students challenges that are not so difficult that students give up, nor so easy that students find the work boring. Finally, mix it up. Provide learning opportunities that use problem-based approaches and project-based approaches. In problem-based approaches, students are given a problem to design creative solutions for. In project-based approaches, students are given choice in how to produce products or develop solutions that demonstrate their learning, as well as having a voice in the way they are evaluated. Now for the STEM practices. Here are the science and engineering practices from the next generation science standards. Asking questions and defining problems. Developing and using models. Planning and carrying out investigations. Analyzing and interpreting data. Using mathematics and computational thinking. Constructing explanations and designing solutions. Engaging in argument from evidence. And finally, obtaining, evaluating, and communicating information. Here are the mathematical practices that comes from the Common Core state standards. Make sense of problems and persevere in solving them. Reason abstractly and quantitatively. Construct viable arguments and critique the reasoning of others. Model with mathematics. Use appropriate tools strategically. Attend to precision. Look for and make use of structure. And finally, look for and express regularity and repeated reasoning. Finally, the book also provides 4 technology practices. But before I list these practices, I want to talk about the definition of technology. The term is usually used for anything that needs to be plugged in, especially a device that is computerized. However, the National Resource Council states that technology is any modification of the natural world made to fulfill human needs or desires. So a hammer or a pencil would be examples of technology. The book categorizes technologies into 6 groups that help students understand the world they live in. They are transportation, construction, electricity, medicine, food and water, and communication. So here are the technology practices. Practice 1. Become aware of the web of technological systems on which society depends. For this practice, help students to think more broadly about technology and emphasize how technologies created by humans are here to serve our needs and desires. Practice 2. Learn how to use new technologies as they become available. Help students learn how to use new technology, how to choose appropriate ones for a situation, and observe how others use technology. Practice 3. Recognize the role that technology plays in the advancement of science and engineering. Practice 4. Make informed decisions about technology given its relationship to society and the environment. When applying these practices, it is important as educators to model the use of words: technology, science, math, and engineering. Here are some examples. What have you learned about the technology of gears? How can we apply the science of motion for this roller coaster project? What is the appropriate math skill that we need to solve this problem? What will you engineer to help transport the items across the river? Moving on, now we will talk about the 3 approaches to integrated STEM: multidisciplinary integration or thematic integration, interdisciplinary integration, and transdisciplinary integration. Multidisciplinary integration or thematic integration is an approach that connects the individual disciplines by organizing the curriculum around a common theme, such as oceans, ecosystems, flight, or even pirates. It provides a coherent learning experience and shows students that you can learn about a topic in different ways, through different disciplinary perspectives. It is recommended that you create a theme based on each discipline's standards, as well as using your students' interests. The negative to this approach is that the connection is only made through the theme and nothing else. No learning goals are combined to create opportunities for deeper understandings. Next, we have interdisciplinary integration. Teachers organize the curriculum around common learning across disciplines. The learning goals from 2 disciplines are fused to form a single key concept or skill. The book provides an interdisciplinary unit example of a science teacher who wants his students to have a better concept of scale, the range of sizes of planets, and the distance between them in space. The math teacher offers to help by having students scale a model of the solar system by using the ratios they are learning in class. The learning goal of science focuses on the similarities and differences between planets, and the learning goal of math focuses on the ability to apply the use of ratios. Combining these learning goals forms a single key skill, which is to scale a model that helps students grasp the size of planets and the distance between planets in the solar system. This integration allows students to go past just learning about the surface features of planets, but instead get a deeper level of understanding of the solar system through size and distance scale. It is important to note that this approach is not entirely distinct from multidisciplinary integration. These 3 approaches differ in the degree of integration. So in interdisciplinary units, the disciplines are identifiable but become less significant than in multidisciplinary approach. Last, we have the transdisciplinary integration, where students embark on real-world problems or projects where students apply knowledge and skills from 2 or more disciplines. These problems and projects also need to be relevant to the students. Teachers should organize curriculum around student questions and concerns, listen to their ideas, and also observe their interests so that students can take ownership of their learning. The transdisciplinary version of the example unit we looked at previously consists of skills and concepts from multiple disciplines. The essential question, or the driving question for the unit, was the following. How would a meteorologist forecast the weather on planet X? This question drives the unit, drives inquiry, and requires the learning objectives to be met for the question to be answered. In science, students would give a weather report from a different planet. They would need to learn how people predict the weather and imagine what it would be like to live on another planet. In art, students would build studio sets for the weather forecasts. In English, students would write out the script for the forecasts, and in math, they would find out how much time it would take for radio transmission to reach them from Earth. All of these learning opportunities from different disciplines help answer the real-world project-based essential question. It is important to note that you don't have to integrate all STEM disciplines in every unit. Project-based learning, or PBL, is very important to transdisciplinary learning. According to the book, project-based learning plus problem-solving equals transdisciplinary learning. There are 3 components of PBL. Essential question, that drives the whole unit. Standard-based STEM learning objectives, that give direction to the unit. And students' previous experiences. Here are some other characteristics of STEM PBL. Students are the center of the learning process. It is important to have students work on decision-making skills and apply their own interests and prior experiences when creating their culminating product or solution. Teachers are more facilitators or coaches who help manage time and logistics. Next, the project is central to the curriculum rather than secondary. They should be broken down into manageable pieces or small tasks and conclude with a product or performance. These projects should involve ongoing and multiple types of assessment with models and rubrics that students can use as a guiding resource. And of course, there should be opportunities for reflection, feedback, and improvements on their creations. For more information on PBL, you will find links to resources in the description below. Now, how do we get started in planning a STEM lesson or unit? Here are the strategies the book provides for implementation. Identify the content standards. Identify big ideas and key concepts. Identify the essential questions or driving question. Establish what the students will know and be able to do as a result of the unit or lesson. Create multiple and ongoing assessment opportunities throughout the learning experiences. Design interdisciplinary learning activities. You will need to decide which approach to use, multi, inter, or trans, that will be most effective for the learning goals. Thanks for watching the overview. I recommend reading the STEM Lesson Essentials book for more detailed information. For links to this presentation, to STEM practices, PBL resources, and more, look in the description below.